Real pleasure and honor to introduce Professor Roger Penrose, who actually doesn't need introduction. However, I'm not sure if everybody is aware of Roger's contribution to loop quantum gravity. So in loop quantum gravity we use spin networks, which had been introduced by Roger a long time before loop quantum gravity, and also those of you who are careful on some mathematical assumptions we make. We often assume that manifolds are analytic or semi-analytic, and this assumption is also due to Roger. Some long time ago, I asked Roger how to solve the problem of infinitely many overlapping loops, and he told me just assume the analyticity. And actually, this assumption we are using. Some long time ago, there was a big GR meeting in Pune, and there was a twistor session there. I was a young, very unexperienced chairman of that session. Roger was my first speaker. There were several speakers. Each of them was assigned 30 minutes. I didn't have my watch, so Roger let me use his watch. He took off his watch, let me use it. I had to be careful because that watch was a gift from Roger's wife, so I had to be double careful with this watch. And Roger started, but his talk was so interesting, so inspiring that I didn't pay attention at time. I let him speak as long as he needed before he finished. And when he was finished, I realized that actually it took him 1 hour instead of 30 minutes. Okay, some speakers were a little impatient. However, Josh Goldberg, who was actually my second speaker, he completely misunderstood what was going on, and he thought that every talk should be 60 minutes long. However, it didn't make him happy at all because he had only 5 slides and he wasn't prepared for a 1 hour talk. So Josh started with a very long introduction. He put his slides aside and he was speaking, waving hands. And after 20 minutes, I had to show him this sign. And then Josh was very surprised. What's going on? I didn't start my talk yet. Roger's talk will be actually, for me, it will be a continuation of the talk Roger gave a few weeks ago in Marseille. The title of the talk, The Palatial Twistor Approach to Einstein Lambda-vacuums. By why continuation? So Roger was giving the same talk in Marseille. However, the talk was suddenly interrupted. At some point, the overhead projector we were using started producing a lot of smoke. And actually, it was out of control. So we had to interrupt the talk. And we hope it's not going to happen again this time. So, Roger, please.
Thank you. Well, if it does, there will be a sign from the heavens that I should stop probing the secrets. Sorry?
Change the subject.
Change the subject, yes. Well, I should explain the subject. This is about twistors, as perhaps you can see. I hope it's all right to pay my respects to Jurek for his wonderful birthday and the conference in honor of this. With a subject which is not his necessarily. It has in common with loop quantum gravity theory, as was just mentioned, is the connection with spin networks. And I think probably twistor theory has now as little connection with spin networks as loop quantum gravity does with the original aims of spin network theory, which was to produce a combinatorial approach to physics, where you just had numbers and integers, I should say, and calculate everything from integers. We've both drifted away from that. I don't know whether we're coming back to it or not. I sometimes hope so. The connection here is that I was looking at SU2 and its representations, and I wanted to do something more relativistic and with space space-time, apart from directions, comes into it. And twistor theory is basically looking at SU22 rather than SU2. The problem is that the representations that one's interested in are continuous and not discrete, and so it doesn't seem very obvious that one has to do with combinatorial notions. Anyway, let me explain certainly very basic ideas about twistor theory, because I have to assume that people are not experts here. And the interesting part, as far as I'm concerned, comes in at the end, when the lightning flash will come down and prevent me from continuing, but we'll see what happens. Should be exciting if it does anyway. I should explain that twistor theory is aimed at it's not a theory which you would think of quantizing eventually or something like that. It's somehow illustrating connections between relativity and quantum mechanics. And you'll see this later on, where it isn't something where you can quite see where the moment is that quantum mechanics comes in or something like that. It's already, they're mixed up together. And they're mixed up together right at the beginning, because the motivations, well, I have a picture, roughly speaking, of what's going on, of a twistor. So we have here a light ray, and it's basically a theory where the light rays are represented by points. And the thing is that what are the points represented by here? Well, you see the space of light rays through a point is a sphere, and it's naturally a Riemann sphere. So the structure of that sphere is like complex numbers with a point at infinity adjoined. So you have a sphere with a conformal structure. And here you imagine that you have perhaps 4 stars you're looking at from this point here, intersecting your light cone, and they would be represented by 4 points. And let's suppose they lie on a circle by chance. Now, if you have another observer whizzing past at a great speed relative to the first one, the point is it's still a circle. So the transformation sends circles to circles. It's conformal and therefore well understood as a Riemann sphere. So here we see one role for the Riemann sphere, which is relativity. And I hope I can make this machine work. Here we go. Here we have another fundamental role for the Riemann sphere, also to do with the directions in space. If we consider a two-state system, and most particularly where that two-state system is a say a spin half particle, and we have spin up and spin down, and the different combinations are spin in some other direction. So again, we have naturally a Riemann sphere to present the directions, but from a different subject. This is quantum mechanics, the other was to do with relativity. So we see that this link between the two subjects is already there at the beginning. Now, I hope I can remember what's on the next slide. That's not it. Another thing about the Riemann sphere, which is also fundamental to the origins of twistor theory, was this idea of splitting your amplitudes into positive and negative frequencies. This was something that was emphasized to me when I was in Syracuse in, I think, 1961, and I shared an office with Engelbert Schucking, and he made this point that one of the key issues of quantum field theory is that you have to split your amplitudes into positive and negative frequencies. And I like to think about this not in terms of Fourier analysis, particularly because if you're in general relativity, you're unlikely to have a nice way of splitting things into your Fourier components. But that's not what you want to do if you simply want to know which is the positive and negative splitting. And the nicest way of doing that is to imagine the Riemann sphere again, and you're thinking of functions which are defined on, say, the real axis, which I've now got as the equator, real axis together with infinity. So this is the equator representing the real numbers, and you have your functions, and if they can be extended holomorphically into one hemisphere, that is positive frequency, and into the other hemisphere, that's the negative frequency. And I rather like this very geometrical way of looking at it, where you don't think of splitting things up into different Fourier components, because that may not be appropriate, but in terms of this analytic continuation into one half or the other. And I was trying to see how you could do this in a more global way for space-time as a whole, and it took me a long time to realize, that this was very much the aim of what I was trying to do, to find a space in which what you could see directly, the real things in a certain sense, were like the real axis, and the extensions into the two halves were the sort of mysterious, complex things which were driving the physics in some strange, mysterious way through the power of complex analysis. So that was the sort of idea, And it took me a while to realize that you can exactly have the same sort of picture where it's not the points now that are in the middle here, but the space of light rays. So we see we have a space which happens to be, this is a CP1, and this is a CP3, complex projective 3 space. And again, it divides into two by this space in the middle. And the space in the middle, the points represent the light rays, including those at infinity. And the light rays space is what you can see directly. And then you have the positive and negative frequency extending into the one half or the other. And that's exactly the way it eventually worked out. Although I may say it took years to realize how exactly this picture was represented by the way that twistor theory developed. So let me try and continue. These are just some formula. I'm going to flash through it rather quickly, so I hope if you know it already, you won't need to see this, and if you don't, you won't have time to look probably. So the basic formula was this thing I call the incidence relationship. The twistor can be thought of as being composed of two parts. They're both two spinners. One is an upper two-spinner with no prime, and the other was a lower one with a prime. And you construct the incidence relation, which we have here written explicitly at the top. Now, when you move your origin, then you have it moves in this particular way, and you have the complex conjugate of a twistor. You have to interchange the two and take complex conjugates of them both. This becomes a dual object, so Z represents the omega and the pi. I should say these are not four spinners in the sense of Dirac theory. It's quite different. They're being used in a very different way. Here we have the complex conjugate, where you take the complex conjugates of the two parts, but you have to swap them around. And the space in the middle, so if I go back to the picture here, the space in the middle, which represents the light rays, is the space of null twistors. Those are the ones where the norm is 0. I hope I can get this right. And ZZ bar, the norm is 0, represent the light rays. So that's the idea. It's also very physically, I want to emphasize that twistor theory is really directly meant to be to do with physics. And many people drift off and increasing the number of dimensions or doing all sorts of funny things, changing the signature or something here. It's very specifically meant to be a theory which is for the physical world. And I want to explain in a short while where the big block has been for about 40 years and where I consider that this block has now been overcome. But I'll come to that shortly. The bottom, we see directly the physical interpretation of a twistor in terms of the momentum and angular momentum of a massless particle. So a massless particle, this is in flat Minkowski space, has a momentum which is p. This is the pi. Incidentally, the reason that I'd make a little bit of a complaint here because people who picked up on twistor theory and used it in scattering and all that sort of thing use the conventions which Ed Witten didn't introduce. He got it from my first paper, where I used all the wrong conventions. And unfortunately, these seem to have stuck. These are the right conventions. You see, the index has to be for the pi, it has to be downstairs, and pi stands for momentum because it is a momentum, and the momentum is a covector, so it must be downstairs. And the angular momentum comes in with the omega, which is a letter commonly used for angular momentum, and that has to be the upstairs one. I had it the wrong way around in my initial paper, without realizing the importance of that, which you see when you do conformal transformations and things like that. Now, the point I make here is that the pi corresponds directly to the momentum of a massless particle, and the two together correspond to the angular momentum, which is this formula I've written here. Let me try and continue, because I'm going to dawdling too slowly here. Now, you see, I want to mention something else. Suppose you move around, you move your origin around to different places, and what do the omegas and pi's do in general? And I've just drawn roughly what they might look like. That doesn't help too much, but this is the picture which tells you how they move around. And this is the origin of the name twistor. This is projected Clifford parallels from a four-sphere into a three-dimensional space, and these represent where the omegas point. In other words, where the angular momentum is. Suppose you have a massless particle with spin, and you want to know where the angular momentum, as your origin moves around, where does the angular momentum point? And the omegas and pi's correspond to the principal null directions of this angular momentum object, and the pi represents the momentum, so they're always parallel, and the omegas move around in this complicated way, which is the picture which is the origin of the name twistor. And the idea, it came from a thing that Ivor Robinson was playing with, special solutions of the Maxwell's equations. And these have this form, which generalized the idea of a light ray to a thing like this when the thing has spin. So the space of light rays is 5-dimensional, that's the thing in the middle, and the space of these objects you can see here is 6-dimensional, so they can twist one way or the other, that's the one half and the other half. So that's the idea. Now what about massive particles? I'm not going to say too much about this, but just say you can accommodate them, and basically the idea, I'm sorry, I've gone to, we have to press the right button here. You can think of a massive particle as being involved with several twistors. Here's a 3-twistor particle. And the idea is it had to do with lepsons and hadrons. I think that we should go back to all this, incorporating the ideas which I hope to get to. I better get to at the end of the talk, because that's the point of the talk. And the idea is to apply these ideas. So these are old concepts we had before of how to build up massive particles. I should say the theory was developed primarily by Zoltan Perez and George Sparling. I hope George is here. And it would be nice to look at these things all over again in the context of how the theory has gone more recently. I won't say...
He will be giving next talk, so
yes, so he must be here sometime. Okay, let me continue. Now this is... I'm not sure the bottom of the picture is represented there. Never mind. I hope you can get the general picture. We are concerned now with massless fields, let's say in conformally flat space, and we have the spin 0 is the wave equation, and the positive helicity correspond to these equations with primed indices and the negative ones with unprimed. That's the way the conventions work. And at the bottom, although you can't quite see it, I've got the different helicities. I don't know if I can make that appear. Yes, how did I do that? Okay, here we have the different helicities, and you can represent them by massless neutrinos or scalar massless fields, or the photons or gravitons, linear gravitons, say, if you're considering a weak field gravity. And the numbers at the end correspond to a twistor function, which I'll just explain on the next slide. So you have various homogeneities, and they correspond, depending on whether you're using a twistor or a dual twistor representation. These are these two columns we have at the end in green, and those different homogeneities come in and represent the different helicities. Let me explain that here rather rapidly. The field equations we've just had, and how do you solve them using twistor theory? Well, you solve them by doing contour integrals. So you take an arbitrary holomorphic function of homogeneity as given in the previous slide. Don't bother to remember it, but the point is that if you've got the right homogeneity, it's balanced by the number of derivatives, or the number of derivatives with respect to the omega, or the number of pi's, and you integrate around a contour. This is more generally what you do, because you imagine your space of concern is covered by a lot of overlapping sets, and that the twistor functions are on the overlaps between the sets. And you have to, the contour integral, if you like, well, I'm usually just concerned with the overlap of two sets, and you can see directly how this gives you the field. Let me not go into that particularly here, but that's a fundamental origin idea of twistor theory. Now, this is just to show that what you're really doing in this previous picture is the things defined on overlaps, but it's really a concept which the check representation is when you have your space covered by open sets and your things are represented as overlaps. But the thing you're trying to get at is the cohomology. And the cohomology is the object which is represented by these particular functions on all of the overlaps. Now you see, this is just to show you what I was being interviewed by a television company, and they're talking about twistor theory, and they said, well, what good is it? And I said, well, you can solve it. You can solve Maxwell's equations with it, you see, electromagnetism. And they said, oh, how about it? Well, it uses this idea called cohomology. And they said, oh, what's that? That should be interesting. There's no way I can explain cohomology. No, not at that level. And then the next morning I realized there is a way, and here's the way you describe it. It's something where the cohomology is the global thing, and you have these representations of it. By piecing this together, you might cut that thing up into pieces, and your cohomology check cohomology element would be telling you how to glue the pieces together, and the cohomology is what you extract from that. And here you see it's this non-possibility of the object. But now you're not talking about a three-dimensional object as represented here, apparently, but you're talking about functions, holomorphic things, and you patch them together, and there's an incompatibility about the thing as a whole. This actually relates to... I haven't got the thing going here. That's it. And it actually does directly relate to physics in a curious way. This is a non-locality that people don't sort of emphasize. I mean, Einstein pointed out a long time ago. Let's imagine that you have a source of a photon, which is the thing at the left here, and you have a screen here, and the screen detects whether the photon it makes a spot, say, wherever it reaches. And the point is that you see the screen here is sort of perpendicular to the line here, which means that if a photon is detected here, then to see that it's not detected here, you see this is the thought. The detection here prevents it from being detected down here. But there's no signal from here to here that can say, whoops, I've seen it, too late for you to see it. But that signal would have to travel faster than light. So that there's something non-local about even this in the representation of quantum mechanics when you start making measurements. So the idea was that you see first cohomology is this kind of non-locality already in the twistor functions. I don't want to continue that here, but that's an idea. This idea continues further. I want to show the thing at the bottom, which is how you piece together now curved twistor space, where locally the patches are flat twistor spaces. The construction at the top is using bundles over this. This is Richard Ward's way of constructing all the self-dual Yang-Mills fields, and which was developed from the earlier construction I had for all the self-dual, anti-self-dual, I guess it is with the conventions, anti-self-dual solutions of the Einstein equations by patching together in this sort of way. Let me be a little bit more explicit about what's going on by going to the next slide. Here we have, at the top, let me just say this. The top picture is flat twistor space, and we have at the right the twistor space, and on the left the space-time, and the points are represented by these Riemann spheres. Now you have to imagine this is a complex projective space, and so what looks like a straight line is really a Riemann sphere. So you have to think as though I've drawn it as a line. This topologically is a sphere. It's a Riemann sphere. And these represent the points in the Minkowski space. Well, it's a complexified Minkowski space. So the points here are these Riemann spheres, which are represented by lines. And the condition for these points to be null separated, line on the same null line, is that these lines meet. So you see this correspondence, which works for a Minkowski space. Now what we want to do, at least locally, well, locally I mean locally for a point here, which means a tubular neighborhood of one of these Riemann spheres or lines here. So that's what I'm considering. And now we forget about the rest of the space. We're just concerned with this local neighborhood of a point in space-time, this tubular neighborhood. And then we want to deform it by cutting it into two pieces. It could be more. You see there's many patches. But let's say just two, which I slide away from each other and glue them back together again. So I preserve the twistor structure, but now there's something strange about it. And what you find is that what used to be the lines don't glue together anymore, so they're broken. So you say, well, where are the lines? Well, you say, well, there have to be holomorphic curves, which are topologically spheres, and which belong to the same continuous family that you started with. And there's a wonderful theorem of Kodara, which says that if your deformation is not too big, then you do have these lines, and we have a 4-parameter family of these lines, and then these lines, each of those, they're the Riemann spheres again, each of those represent points, and you've now got a 4-dimensional space here, and this 4-dimensional space comes out as automatically anti-self-dual, and it satisfies the Einstein equations if you have this projection down like this. Now, this was when I was thinking about Einstein's theory without cosmological constant. If you have a cosmological constant, then it's not just a projection like here, and I should say Richard Ward repeated this construction looking at the cosmological case with a cosmological constant, and instead of having this projection, you have to have this. No, I've forgotten how to move this ahead. Or at least there we go. Now, the infinity twistor is this thing I, which represents the point at infinity, which gives you the space-time, the Euclidean, the Minkowski space rather than the conformal space. And now I've put in, which is not the usual infinity twistors that twistor theorists have been brought up with, but the one where I have a cosmological constant in it. And this cosmological constant took me a long time to be convinced that it's really there, but then I became persuaded, and I'm glad I did, because the things I want to say later depend utterly on the presence of a cosmological constant. If it were not there, and if it were not positive, the thing would not work. So the theory depends on having an infinity twister in which there is a positive cosmological constant. I think that's got missing at the bottom. Can I bring it back? I'm not sure. Yes, I have brought it back. So what we see is not just the infinity twister, which used to be singular. It now gives you a proper symplectic structure. It's a skew thing, which is non-degenerate. And if you contract it onto itself, that's its dual or its complex conjugate, you get the cosmological constant and not zero. And I have this form now at the bottom, which involves the cosmological constant, the infinity twister, both ways up, and you have it in terms of the z's and the w's. What are the w's? Well, the w's are the z bars. They're the complex conjugates of the z's, but now I free them up. So a lot of twistor theory is useful to think of your complex conjugates as a separate variable, and then when you're looking at the real space-time, you make w's complex conjugates of z. But you play around them as being separate, independent objects, and only at the end, when you talk about real space-time, do you make the w's be the complex conjugates of the z's. But still, that is the capital theta is the 2 form, which is now non-degenerate 2 form. You need both bits, you need the cosmological constant, and it took me a long time to realize not only do you need the cosmological constant, but you need both bits. Have all that, then the things that I want to tell you seems to work. Okay, let's continue with this. Now, this is the main stumbling block. For about 40 years, this was what held up twistor theory, as far as I was concerned. Thing called the googly problem. It's a very appropriate term if you know anything about cricket, and I'm not supposing you do necessarily. But this is a ball which is bowled. It spins about its axis. Americans will say, oh, it's a screwball. No, it's not a screwball, because in baseball, the ball doesn't bounce. In cricket, the ball bounces, and so you have to notice whether the spin is spinning right-handed or left-handed, and that's the important thing. And the framework of twistor theory was sort of geared to have it spin one way. And what's called a googly is a ball which is bowled, which spins the other way, even though it looks as though it spins the same way. So it's within the framework of the left-handed spin, how do you describe the right-handed spin? And that's the googly problem, which held the whole subject up for 40 years. I had what I thought was a very beautiful solution, which depended on the cosmological constant being zero. So I was resistant for a long time to the cosmological constant, but then I became persuaded. I think it was Jerry Ostreicher persuaded me it was not just a supernovae, you need it to make lots of things work in cosmology. So now, here's the other thing that we need, the non-commutative twistor algebra. Now you see, I'll come to the reason for this shortly, but it's been a thing which you kept noticing all the way through twistor theory, that there seems to be useful to think about the complex conjugate of the twistor when you're bringing in quantum mechanics or something like that. The complex conjugate really becomes also the canonical conjugate. So we now think of the complex conjugate as a non-commuting object with the twistor itself, and the commutation rules are written at the top. And then you have to make sure that you write your helicity quantity, that's little s, as split into the sum of the two things at the bottom, which I'm not very good at getting this thing to work, so let me, oh dear, what have I done? Here we have the ZZ bar has to split up, and this is the helicity operator. And then your momentum and angular momentum have the commutation rules of standard quantum mechanics, so it ties in beautifully with that. It ties in with the contour integrals I wrote before and all sorts of things. So it's a very natural algebra to introduce the non-commutative algebra where the complex conjugate of the twistor now becomes a canonical conjugate of it. So that's an important part of it. Now, the solution of this googly problem, in my view, came about from a discussion I had with Michael Atiyah, and I was trying to see how on earth you could build up a space of a sort where you didn't have the points. The whole problem was that if you have the points in the twistor space, you have these things called alpha planes, and the alpha planes are the things which give you the thing being anti-self-dual. So you're stuck with the thing being left-handed. And so I finally came around to the view that you've got to have a thing which is a space of a sort, but it doesn't have any points in it. And so the problem is, how on earth do you do that? And you do that using somehow the algebra of the functions. You want to say these are holomorphic in some sense, so you have the algebra of holomorphic functions, and you want to patch the algebras and not the points. And I had this conversation with Michael Atiyah. I said, well, look, how do I make a space where I somehow don't have the space and I want to patch the algebras? And he looked at me and said, well, that doesn't work. And I sort of knew that, because if it doesn't work, because the prime ideals give you the points and all that. But then he said, after a slight hesitation, but that's not true if you have a non-commutative algebra. And I thought, wow, because it's the non-commutative twistor algebra that you have to patch. And that's the key point. So what I'm trying to do is patch together two bits of twistor space in the way whereas before, but it's not the spaces I patch, it's these non-commutative twistor algebras that I patch. And that's the key thing. So that is what palatial twistor theory is about. Now let me try and see if I can describe the ideas quickly. Now you see, one of the things I found troublesome here is that it's algebras. Okay, I can play with algebras a bit, but I don't have the sort of intuition about algebras that I ought to have. But you see, here's the key thing. You can think of these algebras as being the algebras that you get from geometric quantization. Now, the beauty here, I think Nick Woodhouse pointed this out in his book, but let me just remind you and myself what it was about. You see, in twistor theory, you have, remember, the space divided into two, and you have the space in the middle, which represents the light rays. The space in the middle, in projective space, the points represent light rays. But if you think of it as non-projective, then the light rays have a scale. So there's scale light rays, that gives you got a momentum as well. This makes it a symplectic space. And if it's a symplectic space, then you can consider doing this process of geometric quantization, which gives you a sort of quantum algebra. So that's the idea. And what's the first thing you do? The first thing you do is to construct a circle bundle over the space. Thank you. And this circle bundle is, well, the beauty of it here is that if you've got, which I'll call a little p of n, that's the non-projective in the sense you've scaled with a real scale the light ray, so it's got a momentum attached to it, which is a scaling. But now what you have to do for geometric quantization is to introduce a phase as well. And the thing, you've automatically got the phase in twistor theory. That's the beauty of it. It only applies in this number of dimensions, which I like too. It means it only works properly if you're in space-time of 3 + 1 dimensions, which seems to me the right thing to do. And here you have the phase automatically sitting there, because in twistor theory, if you're looking at the twistor as a whole, not just the projective twistor, but the actual twistor, the null twistor the space of these things is a circle bundle over the space of the symplectic space. And so you're in the right place to do this geometric quantization. Now the thing is that this describes things in terms of connections in bundles. So it's geometrical again, and that's something I can nice and see. Now, I have to skim through this, although this is the key part of the whole talk. You want to see how to construct an algebra, which this algebra is represented by these geometric quantization procedures. I only want to mention here a difficulty of understanding, which I have not quite seen the way around it. How do you talk about local things in the algebra? It's a problem because, you see, if you've got functions, it's fine enough. You can say, okay, as long as they converge in the region, that's fine. But the problem here is, you see, you might think, what, e to the z is a nice function, and you have no problem with it, but what e to the d by dz isn't such a nice function. I'm sorry, I can't see how many minutes that was. Never mind. It's anyway, the point is, 5, thank you. The point is that what am I talking about? Yes, it's hard to know what you mean by local, because e to the d by dz moves you out of the set you're starting with. I won't stress that, because that's just a difficulty which I never quite see how to deal with. How do you construct these algebras? Well, I'll have to skim through this rather. Here's the 2 form that you have, which is this thing capital sigma, and that's the symplectic 2 form which you're talking about. And this is naturally defined for any curved space. So if I now think of the space n, it's well defined for curved space-time. It's just the space of light rays, and then a space of light rays with the p scaling, that's the momentum scaling, and now with the circle bundle over it as well. So I have that irrespective of, let's say it's globally hyperbolic space-time, and I don't have to care about twistor theory. I can start doing that. Okay, so that's the idea. But now the point is that locally, I try and bring in the twistors. And now that you can always do this, there's a lot of freedom in doing it, but I don't care about the freedom. The point is, can you do it? And you can do it locally just in an arbitrary way. So you can extend as though there was a little twistor space locally. And the question is, how do you globalize that? Okay, let me continue. This is just the geometric quantize again. And let me say explicitly how you do it. What you do, for some reason it's a two-stage thing, so I can't quite get straight. What you do is okay, you've got your two form, which is this sigma at the top, and you want to construct the connection on the bundle, which is this operator. That's the line underneath it here. And how do you do that? Well, you want to find out what the p's and the r's or whatever they are, the p's and the, what's the other letter? Q, p and q. And so you need your p's and q's. And the way you do it is to say, okay, you take your form, which is a symplectic form, which is the sigma, and you write that, you split your scalar product, which is w dot z, into E plus F. And there are lots of ways of doing that. And if you do it as naught plus that, or that plus naught, those two give you the representation of these operators on holomorphic functions of z, and the other one gives you holomorphic functions of w. But you can split these things in all sorts of other ways, which gives you a representation of holomorphic functions in other ways. So you can represent this algebra in lots of different ways. You want the freedom of doing it in different ways so that you can use that freedom to give an obstruction to doing it globally, which is the sort of thing you want. That's where the curvature comes in. I'm afraid I have to race through this. Now, how do you do that here? Well, let me just see, what am I doing here? Yes. Okay. Now, suppose I'm piecing together these algebras. Now, that's the idea. I'm trying to piece your whole thing together with other patches. And I've got two patches. One patch has your z's and w's. The other one has curly z's and curly w's. Now, you want to preserve all this structure. Basically, you want to preserve the symplectic form. And then you also want to preserve homogeneity. But the symplectic form is the thing you want to preserve. And what you do here is to take a generating function, g. That's the way you do it. You have a generating function. You take half the variable from one side, half from the other side, and you go ahead, and it all works beautifully. That's fine. Now, you see, it does seem to give you, I didn't want to do this part quite right. It does seem to give you a manifold. It doesn't give you the Einstein equations or anything. It gives you, what's curious is that to describe a curved manifold, you actually need to look at these non-commutative algebras. So I was saying at the beginning that somehow twistor theory is all muddled about when you're doing quantum mechanics and when you're not. You see, in order to get a curved space-time, you need to introduce these non-commutative variables. It's not quantum mechanics. It's still classical mechanics, but you're using ideas from quantum mechanics. So I'm just emphasizing that somehow boundary between classical and quantum is all messed up and fuzzed up, which is nice in a way. Okay, now this is somehow you can describe the points by looking at four-dimensional self-conjugate completely commuting algebras. I won't go into that, but you can get the points back out of your algebra. Okay, it doesn't give you the Einstein equations. How do you get the Einstein equations? Well, you bring in this form, and you need both parts, as I said, all that stuff where it doesn't work. I struggled over it for a long time. The zero time, is it? Well, I'll just finish quickly saying what I'm trying to say. This is this, you want to preserve both forms at once. And how on earth do you preserve two different forms with one generating function? Well, I woke up one morning and think there must be a way of doing it, and then I realized that you have a completely crazy combination of coordinates. You don't take half from one, half from the other, a complete mixture of coordinates, and you do that, and then you see that it preserves one for, if it has a certain symmetry, which is swapping these ones with these ones and reversing and those ones. It's very easy to arrange the symmetry. That then the form this generating function preserves both forms at once, so that it does give you the preservation of both forms. And is that the end? Not quite. This is, well, it is the end more or less. I just want to say that what this gives you, what it seems to give you, is a general prescription for the general Einstein Lambda-vacuums. Now, when I say a general prescription, you can't write it down as ds squared equals something or other, because you've got to go through all this rigmarole. You can produce with the generating functions gamma of this form with the symmetries, which I hope I've written down correctly just underneath it. When you impose those symmetries, this gamma will preserve both forms at once. And then you can construct your points. Well, that's where the difficulty comes. You have your algebra, and in this algebra, you look for those subalgebras which are four-dimensional, completely commuting, and self-conjugate. Yes, there was a gift from God, I should mention here, was that this thing was to preserve both forms. But you see, what you couldn't do with the original way is to say what you mean in a Lorentzian space. You've got to impose the hermeticity, that W bar is equal to Z. How do you preserve the hermeticity? I have no idea in the way I did it before. But here you can do it immediately, because you look at these things and you see that it's already, the hermeticity is already within one generating function. So you can explicitly represent that too. So you can make it be a Lorentzian space, and it preserves both forms, and therefore the points are these completely commuting self-conjugate four-dimensional subalgebras. And my roommate Keith Hannibus, I asked him, in Minkowski space, does this work? And he came up with a nice proof. Yes, it does. It gives you the right answer. And it seems to me unlikely that it's the wrong answer when you curve the space, because you get these algebras. The point is that, do they define the points? Well, it's unlikely that in general you get more all at once. The last comment I wanted to make is, okay, this isn't quite the whole story, because I've treated these two forms differently. One of them is to give you a connection in a non-commuting algebra. The other, I haven't done anything with it. Now, does that give you a theory of quantum gravity? So that is really the idea. Maybe it does, because you have now a commutation rule between this is the other form now, the theta form. When you try to quantize that, do a Dirac quantization on that, you have non-commutation rules, which I've written down at the bottom. Now, does that give you anything like a quantum gravity theory, where you have these non-commuting variables where not just the z's and w's have a commutation rule, but the z's and z's and the w's and w's have a commutation rule? And that would be fascinating to look at. Does this give you something like a quantum gravity theory or not? It would be very intriguing to see. Thank you very much.
Questions or comments? Carlo.
Sorry, can you repeat that?
I lost the last point. Why does the preservation of theta give the Einstein equation? I lost that point.
Yes, because I didn't explain it. Yes, you see, you've got these two forms, and the Dirac quantization of the sigma form gives you the commutation rules between the z's and the w's. But the z's commute with themselves. Now, if you do the Dirac quantization procedure, that is to say, you look at the Poisson brackets that symplectic form gives you, that's the dual of it, and then that gives you commutators by Dirac quantization, and then that's the expression I've got written down at the bottom here. That comes from the Dirac quantization of the Poisson brackets that are the dual of the symplectic form theta, which I wrote down. So this is the place where, if it is giving you quantum gravity, you see, before this, it was quantum ideas, but it was purely classical general relativity. That's the idea. Whereas if you're trying to extend to a quantum thing, you have to do the commutation rule on the theta, not just the sigma.
So what we're saying is that there are no further equations.
I'm sorry?
There are no other equations.
No other equations.
That's the point, somehow.
Yes.
Okay.
That's right. No, these are the equations. Well, I mean, there are no matter fields in this. See, if you want to bring in matter fields, you'd have to put several twistors, I suppose, I had a quick slide earlier on showing you how you might expect to put massive fields in here. But this is all vacuum. Yeah.
If I can make a comment, in Minkowski spacetime, coordinates play a little different role than on general curve spacetime. So they know about metric tensor. They are actually built from the notion of distance. So if we consider generic coordinates in curved manifold, then they don't encode dynamical fields. So if they were supposed not to commute, then they should use metric in their definition. So they should be somehow adapted to given metric tensor.
To the metric. When you say the metric, I should have explained that point a bit better too.
I guess you in your case metric is some secondary.
No, yeah, but you see this again. I didn't stress that point, but it's a good point. You give me the chance to stress it. You see, in twistor theory, it was already a bit surprising with the old nonlinear graviton construction, none of this palatial stuff. In the old construction, if you wanted to introduce a metric, not just the conformal structure, what you do is basically put the infinity twistor in, because that gives you the infinity twistor is what gives you the metric and not the conformal structure. But it also gives you the Einstein equations. See, when you preserve it with the patching together the two pieces of twistor space, you automatically get the Einstein equations even with the metric. So they come together. And that's what happens here as well, which is quite curious. The metric comes in with this form theta. That's the first time you have a metric, you have a distance notion. And at the same time, you get the Einstein vacuum equations. But it's not as though you have two separate stages. You might say, okay, I think that's your question. You want to put the metric in. The way you put the metric in is with the infinity twistor. That's always been the way you did it in twistor theory. That gives you the scale. Here you put the metric in, it gives you the lambda as well. So it's not Minkowski space, it's de Sitter space, if you like. And the metric comes in with the introduction of the theta form. But then the quantization procedure, or if you like, it gives you this thing here, and well, even before you do that, you get the Einstein equations. The Einstein equations come along with the metric, which is sort of curious, but that's what happens with twistor theory.
It's fantastic.
Yeah.
Thank you. If there are no more questions or comments, let us thank again.